Hello directors, this week we are talking about curved lines, and it looks a little scary, but it's not going to be. It's going to be a lot of fun. Okay, so let's get started. The first thing that we do for the first 5 minutes is a warm-up, and we're now moving into the interesting integer concept. And basically all that means is that you're picking a number, and you can use the handout that CC has given. If you go into the, last year in the CC Connected on the companion, when you went to the tutor page and it has the little link where you can watch the tutor video or see the little tutor lesson plan stuff, and then there was a link for interesting integer, and it had 10 weeks worth of example numbers to use. That's what I just went from last year. And so you can use any number you want, but if you don't want to have to kind of like go through something and make it up, then I would grab that worksheet and it will help you be able to get started. So the interesting integer for the first week is the number 1. And so what I did is set a timer for 5 minutes, and then I just said, what can you guys tell me about 1? And so if they're not talking a lot because they don't get it the first week, you can say, well, how do I write that out as a word? Okay, 1 is spelled like this. And then somebody might say, well, in a Roman numeral, it would be an I. And in a tally mark, it would also just be 1/. And I don't, sometimes my kids would tell me in Spanish or French how you would write it or say it. They might say how 1 is really cool because no matter what the exponents are, it's always just going to equal 1. And we could talk about the identity law. There's a lot of things that you can do to talk about 1 and how 1 is important. Or what would you want to say about 1? Sometimes kids would say, well, and it's all involved with straight lines. There's only straight lines in 1. So sometimes your artistic kids are going to find other things that are not as math related, but it's a different way to look at the number 1. And that's great. I love when they would make other comparisons like that. So just let them talk about 1 for up to 5 minutes. And so after you finish that 5 minutes, and sometimes if they don't have 5 minutes worth of stuff, I just moved on to the cover page because there is so much math this week that it is fine if we didn't have to spend a whole 5 minutes just kind of warming up their brain. So the next thing to move into is the cover page. And the cover was really cool. I had a student who had been to Monet's house and these gardens and got to actually see not only the painting, but got to see or a number of paintings, but got to see the actual bridge and the place where Monet had lived, where he painted that. So it's a Monet piece, if you didn't know. You can ask the kids what they think about it, what do they notice on the image, or what do they see? And they'll probably mention how there is a bridge, and the bridge has curved lines. They might talk about the flowers and other images and stuff like that. So I would just let them talk about that. Definitely you can see the curved bridge though, which kind of ties into curved lines. Then the quote, you can go ahead and read out the quote, and I wrote in my notes, our quote discusses curved lines versus straight lines. Straight line of duty can be hard. We don't always want to do the hard things, right? But Jesus tells us in Matthew 6:33, but seek ye first the kingdom of God and his righteousness, and all these things shall be added unto you. So the importance of doing hard things and remembering that we grow from hard things. So sometimes when things are hard, like the student pages are going to be this week on their workbooks, we remind ourselves that God wants us to work on things and do hard things and show how capable we are. And then the reflection is a good reminder of the importance in learning and seeing how all things tie to him, meaning Christ. So there's a good reflection of that in that statement. And then you can ask if there's any other thoughts on how it ties to curved lines. I skipped saying we also go to that compass page. That's the compass page. Say where we at. We're in 2 dimensions still. They can see that on there. They can check that off. And you guys are in monomial or complex, and they should be able to see how that is on there too. And then now we're ready to move into the dialectic. Okay, so they have the open-ended question, tell me everything you know about curved lines. Like I've said before, I didn't find the open-ended questions got my kids talking, so we would usually just kind of go through some of the lesson stuff and then see if they have comments and questions from there. And so the first for the 5 common topics is comparing straight lines to curved lines. And so before, a few weeks ago, we were dealing with straight lines, and we had okay, that's my poorly drawn straight line. So we had our straight lines, and we talked about slope, and we talked about the slope line equation. So that was a few weeks ago, I think. And then, but this week, and so we would have things like a constant where our slope hasn't changed. But this week we are talking about a bunch of different curved lines. The first one that they actually start tackling in their workbooks are exponential lines. And so you can have an exponential increase when you plot your exponent. So this is saying something like, kind of like y equals x squared. So this is the idea when x is 2, y is 4. So 2, well, here, I'll just plot this for you real quick. And maybe you could plot it for the kids too to show them what an exponential line looks like. So in this case, if I said x was 2, 2 squared is going to be 4, so my y value is 4. So 1, 2 on my x, 1, 2, 3, 4 on my y. So that is the point 2, 4. This is my first point to plot on here. How about if I looked at 3, plugging in 3 for x squared will be 3 squared, so y will equal 9. 1, 2, 3 over on my x, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3, 9 would be up here. If I kept plotting out numbers, I would notice that I do not have this nice straight line. I have a line that goes like this. So this is my exponential increase line, and it is at a curve. And so this is why the exponential graph is the first one that they look at. It's an example of a curve, and it's something we've talked about before with the exponents. So it's kind of hopefully an easy one for them to see, a curved line. In this case, when our exponential line is going up like this, we would say this increases, or we also call that growth. So, you know, hopefully our retirement portfolios are doing this, right? Or you could have where your exponential graph is moving like this. You might see this in populations of animals going extinct. So this is decreasing exponentially. We also call that decay. Okay, so that's an example of decreasing. On a case where you are decreasing the base of the equation, so they give a really simple equation of f of x, here I'll write it down here, f of x equals base with some sort of exponent up here to a certain exponent. So if your base is a whole number, so 2 or 3 or whatever, you're going to be increasing like this increasing growth. But if your base is a fractional amount, say that your base is 1/2, and then you can still have exponents, values in here for exponent, you're going to see a decreasing or a decay. So when your base is between 0 and 1, you will have the decrease or the decay. And when your base is greater than 1, you will see the growth, the increase or the growth. There's a more complex equation for this, and they actually have it in their student problems. They don't really need to understand what that all means. I went over it on my Math Explorers program, but for the most part, all they need to do is recognize where there's certain values in the equation and then how they find those values. They don't have to calculate to find them. They just have to look at the equation and say, oh, my base is written right here, and in this equation, the number that's right in that spot is a 2, so that's my base. So they're just trying to match it like that. Okay, the next thing, definition. And so I have define limits. And we actually talked about this when we kind of introduced some limit stuff a few weeks ago. I just had forgotten, I didn't have it in my lesson plans until this week. So if you haven't talked about limits with your class, maybe it's a good time to do that. And so the idea is a limit is where we approach something, but we don't actually get to that point in time. And so because Halloween is nearby and some kids might be doing trick-or-treating and candy and stuff, it seemed like, and there's a lot of candy in the stores, it seemed like a time to use candy as our example. So I could say if my kids are eating their Halloween candy, they really want to eat a bunch of candy, but at some point they are going to hit that limit, and then they're going to be sick if they ate too much candy. So their goal as a kid is to eat as much candy as I can possibly enjoy, but not get to that point where I hit the limit, because then I'm going to be miserable. So you're trying to get smaller and smaller and closer to that limit, but you don't want to actually reach that limit or hit that limit. So that's a way to think of limits. You're trying to not actually get to that limit. And then the other example that I gave for my kids in class is walking a bridge. And this is going to tie more to your approach, how you're approaching those limits. So we could say that this little gap here is like my limit. I don't want to get to this actual spot, because I can approach the limit, but I don't want to step right here, right? Because I'm going to fall down. I don't have any land right here. So the same thing is kind of happening with limits. We're approaching, and if I'm walking from here, I would say that I'm approaching the limit from the left. And when we approach the limit from the left, we have a little negative sign. Over here though, I have somebody else. And they are approaching the limit. Remember, our limit is kind of reaching this part right here. They are approaching from the right. Approach from right. And that would have a positive. So they're going to see examples where in their problems where it talks about reaching the limit, and when it has a little negative, it means they were approaching from the left. And when they see that positive up there, it says that they're approaching from the right. So they're kind of approaching this limit. But again, we don't want to hit the actual limit. In terms of the graphs, this might be a weird way to see it on here, but in terms of the graphs, when you are approaching a limit and you have a value you cannot actually hit, like let's say your equation has it where 0 is not a valid number, you would have a limit at, you would have an asymptote, at 0. So an asymptote, we're going to actually see this on the graph, but the asymptotes are shown on the graphs. They're these dotted lines, and it just means that you cannot have a value at that exact number. So asymptote means you can't actually have a value at that number. So that's all you really need to know it means right now. That's all the kids really need to know for now too. Let's look at this graphically so that I can explain what I kind of did in pictures, but with some actual math behind it. Okay, we're going to start with an equation. So I have here f of x equals x minus 4 divided by x minus 4. What do we have when we have a value divided by itself? They come back in total 1, correct? So in the math map, they actually will draw a green box around something like this, because they want the kids to recognize that when you have something and you're just dividing by itself, this is just going to total 1, okay? Simple enough, we've seen that before. This is mostly true, but it isn't actually going to be true at the point where x is exactly equal to 4. And let me show you why. Because if I plug in 4 minus 4 divided by 4 minus 4, I'm going to end up with 0 divided by 0. And we cannot divide that, right? We cannot have 0 divided by 0. If you plug that into your calculator, it's going to say error. The other way is that you would say it is undefined. So this is undefined. It's kind of like that gap that we had in the bridge that the people were just walking on. So at the point of 4, this equation is not going to work. If my x was equal to 5, the equation works. If my x is equal to -2, my equation still works. The problem is exactly at the point where 4 is at. So we're good after 4, we're good coming up to 4, but we're not good at the exact value of 4. So if I were to plot this actual graph, let's see, 1, 2, 3, 4. Okay, this is my point where x is equal to 4, so I'm putting a circle here because I cannot have that value on here. But I could keep going in this direction and I could keep going this direction. So my x can be any other value, but it cannot be the value 4. So right there at 4, it does not work. And so I've put an open circle right there. So I cannot have the value 4 here. I would say though that in this direction, you would say x approaches 4 from the left. See how I wrote that little negative sign over there? And on this side, I could say over here, this way, x approaches 4 from the positive side, from the right. So x is approaching 4 from the right, and on this side, x was approaching 4 from the left. That's what that little negative indicates right there. So that's how you write that on both cases, and then right at the point where it's at 4, it's undefined. It doesn't work right there. We would also write this out and say that the limit of f of x as x approaches 4 is 4. So that is our limit. We can't actually reach that value. Okay, the next thing on the 5 common topics, it says, how do the circumstances of dimension change how we visualize limits? My notes say, look at the bottom of the page on how limits adjust in 1D or 2D. Oh, okay, so here was an example of one dimension, because it's kind of like we have a straight line. We're approaching from the left, we're approaching from the right. But once we have 2 dimension, and we can move both in width and our length, then we can start having other limits, and then we can end up having asymptotes where it cannot have a value at that value. So, oh, and that's my next thing to talk about. The relationship of independent variables and dependent variables at the asymptote. So let me draw out a line. Oh. I'll have it go to there. Okay, so in my case right here, I have a function, I have graphed, but I have a value where it cannot have a value in here. And so I would say that right here, I have my horizontal asymptote, and that is spelled asymptote. And that asymptote is right at this point, so that is y equals 1. So at y equals 1, for this particular function that I've graphed, it's not the same function we looked at before. So here, let me just erase that so it's not confusing. I don't have an equation written up here for this, but let's just pretend that this is my function. And at this one point, I cannot have a value on here. So I would say my asymptote is at y equals 1 right here, and it's drawn right here. So the asymptotes are drawn with dotted lines. It means we cannot have a value at that point. That's all that it means. This is an example of a horizontal asymptote. You can also have examples, and it's usually at the point of the y-axis or the, yeah, so here, let me let me dot this so it looks like it's dotted. Okay, so this is a point where the y-axis is the asymptote. And so you could have some sort of function that is approaching, but it can't actually reach those values. And so you could kind of say it's like it's approaching infinity. It's not exactly. It's really that it's undefined. It can't get to that exact point. So you're seeing where the limit approaches, but it can't actually reach that point. So it's never going to reach a value that crosses over this y-axis, your function. So this asymptote is right there with the dotted blue line. And this function is not going to cross it. Okay, and then the last thing, the authority question for 5 common topics. How does the asymptote provide a visual truth for the graph? It's showing us where our values cannot apply or where our values cannot be at. It's letting you see where the limit approaches. Okay, the next page, the memoria and arrangement page. Oh, okay, this page is really fun. It has a lot of graphs. They don't need to know all of these graphs right now. I think if you're going to focus on the ones that are the most helpful, it's the polynomial ones. So, okay, so I've drawn actually, let's see, my lesson plan has 5 common ones that they're going to talk about. They're also doing exponential graphs on their problems, so that might be useful. But they should hopefully start to be able to recognize that a constant graph looks like this. A linear graph looks like this. Doesn't have to go through the origin. I'm just drawing it that way because we see it. It could be up here. That's just, other things will tell us where it would place on the graph, but the simplest is to just have it go through the origin. A quadratic has a parabola like this. That's when we have something like x squared. And then a cubic is where x has an exponent of 3, and those graphs look like this. Again, they don't always have to look like this. It could be, if you end up having it be negative, it's going to be flipped. And so it would look like this. So if they can just start to recognize what a cubic graph looks like, then once they see that type of graph, they'll say, hey, I'm looking at a cubic graph. And when they're in pre-calc and they're solving something and they don't get a cubic looking graph after they've solved their problem, then maybe there's a problem. So helping them they don't need to know all the math on this stuff yet, but just helping them say, this is a constant line, this is a linear line, this one is a cubic line. Absolute value looks like a V. Right? Because your values are always positive. And so your absolute value graphs look like this. So they should be able to start recognizing stuff like that. That's what you're trying to get them to do this week. And then in terms of the charts, so the charts do have all the answers to what they need for their workbooks. The thing to know about the student pages is for them to just focus on looking at what the graph is and then realizing that they're given an equation and they're just trying to pull out the stuff that is being discussed. Let's talk about one more thing real quick, which is how the concept that different equations produce different graphs. And that's the big thing for them to know this week. And the other thing to go over with them that I think is helpful, because this isn't really in those first Memoria pages, but I think it was a nice thing to discuss in my class, because they do have a lot of problems on their school books with this, or their student pages. Okay, so if we have a curve for our graph, and this is more like a sine or a cosine curve, which they're not doing a lot of yet at this level, but you could have a curve where you only have part of this in your graph, or you could have a curve where you have multiple mountains and hills and stuff to it. So we're just going to go over some vocab with this though. When you have a curved graph like this, we call this point the maximum. So you can guess, we call this point the minimum. We say that this is concave down. because it's concave and it's arrangement, how it's laid out, and then it's pointing down. So concave down, this one is concave up. At the point of your graph where you are going upward like this increases. And when the curve is moving in a downward direction like this decreases. The concave down and the concave up at that midpoint where it changes concavity from being in one direction to being the other, we call that the inflection point. Okay, I think that's everything that they really have to label on their in their booklets this week. And then there's some other stuff about how the increases happen. Okay, I don't have this, but you can have a slope like the exponent slope where we are increasingly increasing. So we are increasing at a greater rate as we continue along. So we would say this increasingly increases. Versus if you're increasing, like you're going upward, but you don't keep increasing by that strong amount. You were really increasing here, but then you're just increasing a little bit, and then you're increasing just a little bit more or a little bit less. So you're still going in an upward direction, but you're decreasing the amount that you're doing the increase. We call this decreasingly increases. Increases. But they're both going up, so their action is still increases, versus heading down like this, the action of this curve is that it decreases. And it is steeply decreasing. So it decreased a little bit, and then it really decreased, and then it super decreased. It's going even more extreme. It increasingly decreases. Increasingly decreases versus versus this one has a sharp decrease, but then it's a little more subtle, and then it's a little bit less, and so we would say this decreasingly decreases. Okay, so it's a little bit harder. It was easier when we were dealing with straight lines, and we just said we either increase or we decrease. Now we have to think about how we are increasing. So we've added on these adverbs, but if you put some pretend numbers into your mind, you could kind of see how, these numbers would be increasing as we keep going along, and these numbers would be decreasing, that change. So you can try to work it out that way. Go through aha moments of the last week. I did not have my kiddos do all 4 pages and do the tops of the pages. It is pretty intense, the level of kind of what they're going through and how they're trying to understand this. So I would just pick, you could maybe try to do the top of the first page and the top of the second page, or just parts of the first page or the second page. The first page that you're seeing looks like this. You have exponential curves. So it's useful to kind of show them the exponential curves. They're seeing the more complete equation that you would have for an exponential function, and then they're just kind of trying to pick out the values when they're given the function of what's the a value, what's your base value, stuff like that. Do you see an asymptote? So those dotted lines, there's my asymptotes. So that's what they're doing on that. You may just want to help guide them through that, or they could work in a big team to try to go through that. The other thing, you might want to consider doing the second page also if you can, or maybe just the second page, because it's really nice that they see a constant line, they see a linear line, which should be a repeat from before. We've seen those before, but then they're going to see a parabola for a quadratic, and they're going to see a cubic. So the exponent is a 3. So you can kind of look through those 4 types and then label them, and again, you're finding those a values and the k value. So I don't know. I would say if you can get through at least one of those pages, it would help them see how to do it when they go home a little bit. I don't think that it would be very reasonable to try to get through all 4 tops in that time, because it's a pretty heavy duty lesson. And the big thing to know is, just like with IEW, we do the easy plus 1. So if you have a kiddo, or if you want to tell other parents who might be looking at this week saying, I can't do this, I can't work on this, you know, if they can just focus on starting to see what some of the shapes are for the graphs. And I wouldn't worry too much about the geometrical stuff down here at the bottom, the sine and cosine, because they're not really doing that at the monomial and complex level. They have a very few problems on that, like 1 problem. Mostly they're dealing with the upper stuff. So if they can just recognize what type of graph they're looking at, great. And maybe the equation stuff is over their head and they can't quite get it. Some of the kids will be able to see some of the patterns on the equations and pick out some stuff. The reality is, this is pre-calc material at its full blown scale. So the kids should all be hitting this in high school, because they should all be getting up to pre-calc, but they don't have to know it all right now. They have years to try to keep building on it. So if we can just help them understand something that is understandable for them at this stage, which might just be the image of the graph, great, because that is the whole easy plus 1. And then maybe next year they can actually look at the equation and pick out what some of the things in the equation mean. And maybe the year after that, they'll understand more of the equation. And then by the time they are a junior in high school, they've looked at these graphs, these images, they've looked at the equation, and they're like, yeah, I can calculate this stuff. I've been looking at this for years. So that's the goal. Just remember, it's okay to do easy plus 1. So just like we do in IEW, use that philosophy for the math map, because it will really help out. Okay, and another plug for my Math Explorers, we do go through the equation. I try to show them what the different parts of the equation mean, how something is showing us where our vertex is for the minimum point on a quadratic formula and a parabola on the problem. And it's like, try to just show them why we're getting certain equations. Still probably going to go over the head of kids, but some of the kids are going to pick up on it, and next year the other kids who aren't getting all parts of it will understand a little bit more. So hopefully that's the case. If you have questions, please feel free to send me messages or ask, and hopefully I can help you out. And the math map, they're always available for questions too. Okay, thanks for watching. I hope this wasn't crazy. I hope it helps kind of make sense of it.